Hello, my name is Naomi Pineda, and today I will be talking about the D block element silver. So, throughout this presentation, we will be going over the following objectives. So, we will explore various methods for extracting silver from ores, study the chemical and physical properties of silver, examine the relationship between silver and other elements, identify at least 4 applications of silver, explore a case study of silver nanoparticles in medicine, investigate the potential negative effects of silver on cells, review 6 analytical methods for studying silver, and identify 3 academic journals for further research on silver nanoparticles. The importance of silver lies in its versatility and unique properties, which have allowed it to serve a variety of purposes throughout human history. Its shimmering beauty has made it a sought-after material for jewelry and decorative items, while its physical and chemical properties have led it to use in modern applications such as electronics and medicine. Additionally, silver's occurrence in nature and extraction methods provide valuable insights into the Earth's geology and mining practices. Understanding the physical and chemical properties of silver, as well as its potential environmental impacts, is crucial for maximizing its benefits while minimizing any negative effects. Overall, the continued importance of silver in our world is rooted in its ability to adapt to changing societal needs and to contribute to human progress in a variety of fields. Silver is often found in association with other metals like lead, copper, or zinc in various metals. The process used for extracting silver depends on which metal is present in the highest concentration in the ore. To extract silver from copper ores, copper sulfide concentrates are smelted and converted into blister copper, which contains most of the original silver content. Electrolytic refining is then used to remove any remaining impurities. In the case of lead ores, lead concentrates are roasted and smelted to produce lead bullion. The Parkes process is used to purify the lead bullion, and cupellation is employed to segregate oxidizable lead from the elemental gold and silver. The end product is an alloy of gold and silver, which is subsequently refined utilizing the Mobius and Thumb bulb back method. Any remaining silver is affinated to concentrate gold and then refined using the Woolwheel process. For zinc ores, the process involves roasting and leaching with sulfuric acid to extract the zinc content. The resulting residue contains lead, silver, and gold, which is then processed through slag fuming to remove zinc. This results in lead bullion that dissolves the silver and gold, which can then be refined. It's important to note that each method has its own specific process, depending on the type of ore and concentration of the metal associated with the silver. Understanding these processes is crucial for efficiently extract silver and other valuable metals from the ores. Silver possesses unique physical and chemical properties that make it useful in various applications. Its malleability and ductility allow it to be molded into various shapes and drawn into thin wires easily. Silver's high thermal and electrical conductivity make it an excellent conductor of heat and electricity. Its high reflectivity makes it useful in mirrors and reflective coatings. As a noble metal, silver is resistant to corrosion and oxidation in air or water, but it can react with sulfur compounds in the air to form silver sulfide. Silver is highly reactive with halogens such as chlorine and bromine, forming silver halides. It also reacts with nitric acid to form silver nitrate. The physical and chemical properties of silver are largely determined by its atomic structure. The tightly packed arrangement of its atom in a metallic lattice and the metallic bonds that hold these atoms together enable the transmission of both thermal and electrical energy, contributing to its malleability, ductility, and conductivity. The high reflectivity of silver is due to its loosely held outermost electrons, which can be easily excited by incoming photons of light and re-emit the photons, resulting in reflection of light. Although silver is commonly found on its +1 oxidation state, it can also exist in states +2 and +3 in chemical reactions. Silver is highly soluble in hot concentrated sulfuric acid, nitric acid, and oxidizing acids, and can dissolve in solutions containing cyanide ions when oxygen or peroxide are present. Due to its distinctive chemical properties, silver can form unique compounds with various elements despite sharing a similar electronic structure with copper. Some common compounds formed with silver include silver nitrate, silver chloride, silver bromide, silver iodide, and silver sulfide. Silver is a versatile metal used in jewelry, electronics, and water purification. It's an essential component in printed circuit boards due to its excellent electrical conductivity and reliability. At the nanoscale level, silver has exceptional properties for drug delivery and diagnosis. While it can eradicate bacteria in water, its safety is not yet fully established. In the study titled Silver Nanoparticles Biosynthesized by Ana Baena Flos Aquae Enhance the Apoptosis in Breast Cancer Cell Line, researchers explored the potential of using silver nanoparticles as a treatment for breast cancer. The study found that silver nanoparticles can be synthesized using Ana Baena Flos Aquae biomass extracts in an eco-friendly and cost-efficient manner. And the green synthesized silver nanoparticles showed potent anti-cancer activity against T47D cells by inducing apoptosis. These findings have significant implications for advancing the field of nanotechnology and cancer therapy while promoting sustainable development. The production of silver nanoparticles has significantly increased due to their emerging applications. However, when these particles reach underwater sediments, they can undergo chemical alterations like oxidative dissolution, sulfidation, chlorination, and reduction. Additionally, they can interact with natural organic compounds. This accumulation of nanoparticles in sediment can have negative consequences on marine life. Therefore, it's crucial to examine the ecological consequences of silver nanoparticles and take necessary measurements to limit their spread and release into the ecosystem. Silver nanoparticles can have toxicological effects on both the environment and human health. Silver nanoparticles induce oxidative stress, endoplasmic reticulum stress, and mitochondrial function damage in living organisms through non-reactive oxygen species pathways. Silver nanoparticles can disrupt mitochondrial function, induce mitochondrial DNA damage, and alter mitochondrial membrane potential, leading to the release of mitochondrial cytochrome C and ultimately apoptosis. They can also disrupt calcium homeostasis and activate the unfolded protein response, leading to the endoplasmic reticulum stress, endoplasmic reticulum associated degradation, autophagy, and apoptosis. Furthermore, silver nanoparticles can induce mitochondrial function damage, impairing energy metabolism and releasing reactive oxygen species, which can lead to cellular apoptosis. Therefore, it's essential to understand the toxicological effects of silver nanoparticles and take necessary measurements to limit their potential impact on the environment and human health. The amount of silver in different samples can be determined using various methods, including graphite furnace atomic absorption spectrometry, atomic absorption spectroscopy with a microcup assembly, high-frequency plasma torch atomic emission spectroscopy, flame atomic absorption spectrometry, scanning electron microscopy in conjunction with X-ray energy spectrometry, and neutron activation analysis. These methods are used to quantify silver in different matrices such as blood, post-mortem liver samples, tissues of patients with various health conditions, and biological and environmental samples. Each method has its own advantages and limitations, and their selection depends on the nature of the sample and the required sensitivity of the analysis. Research on silver nanoparticles has been expanding in recent years due to their potential applications in various fields, including biomedicine, electronics, and environmental remediation. Silver nanoparticles have unique physiochemical properties that make them attractive for these applications, such as high surface area to volume ratio, antibacterial properties, and plasmonic properties. There are numerous resources available for expanding on research related to silver nanoparticles, including scientific journals, conferences, and databases. Some of these prominent journals publishing research on silver nanoparticles include ACS Nano, Journal of Nanoparticle Research, and Nanoscale. Overall, with the increasing interest and potential applications of silver nanoparticles, there are ample resources available for researchers to expand their knowledge and contribute to the field. Here is a list of my references, and thank you so much for listening.